This is the demo for College Algebra Lesson 17. We're going to be creating new functions by combining two or more functions through the operations of addition, subtraction, multiplication, and division. Luckily, this is pretty straightforward. The only sort of tricky thing is that the domain of the result, when you do a sum, difference, product, or quotient, is always going to be the intersection of the domain of f and the domain of g. So it's just all real numbers that can go into both functions. And it's pretty straightforward in terms of the arithmetic. If you want to take the sum of f and g, it's just f of x plus g of x. The difference is f of x minus g of x. The product is f of x times g of x. The quotient is f of x over g of x. And we have an additional restriction on the domain in that g of x cannot be 0. Okay, looking at an example, I have f of x and g of x, 1 over x minus 2 and the square root of x, and I want to find each of the combined functions and their domains. Okay, so to help us find the domain for all of these, I'm going to calculate the intersection of the domain of f and the domain of g. So I'm going to start by drawing the domain of f. So f here, the domain is all real numbers except for 2. You can plug any x you want into this formula except for a 2, because a 2 would make the denominator 0, and that's not allowed. Okay, so I'm going to put, here's 0, here's 2. So I put a big open circle on the 2, but I can shade everything else. Okay, so that's my domain of f. The set of all x's such that x is not 2. Okay, the domain of g would be only positive numbers or 0. You can put a 0 in here, and you can put positive numbers in here. You can't put negatives in. So here I would say 0 to infinity is the domain. So when I graph that, here's 0. I'm going to include the 0 and shade everything to the right. Okay, and then the intersection is everything that these two have in common, all of the overlap. So any place that is shaded for both lines. So it looks like 0 to infinity is good. Both is shaded, except for the 2. I have to leave out the 2. So let's see, I'm going to put 0 on and include the 0. And here's my 2. I have to leave that out because it's not shaded on both lines. So there is my domain for the intersection, and it goes from 0 to 2. I'm going to include the 0 because it was included in both f and g, so it's included in the intersection. So when I write it out in notation, I put a square bracket, 0. I'm going to go to 2, and then I'm going to put a round bracket because I can't include the 2 in this domain. So I put a round bracket to jump over it, and then I put union 2 to infinity. And that's going to be my domain for the sum, the difference, and the product. So I'm going to write that in these 3. I am not going to write that domain for f over g because f over g has an additional restriction in that g can't be 0. So we'll think about that domain when we get here. So adding, subtracting, multiplying, and dividing functions, f plus g, we're just going to replace f with its formula and g with its formula, and we get 1 over x minus 2 plus the square root of x. And I'm not going to bother simplifying that. I'd have to get a common denominator, and it actually wouldn't look any simpler than it does now. So f minus g will be 1 over x minus 2 minus the square root of x. F times g would be 1 over x minus 2 times square root x. This one I am going to simplify because I can make it look significantly simpler in one easy step. So I'm just going to write that as over 1 and multiply the fractions. So I get square root x over x minus 2. And then f over g, I have 1 over x minus 2 over the square root of x. And now when I think about the domain of this, it's going to be related to this, but I have an additional restriction in that this denominator, square root x, can't be 0. It's in a denominator now, so this can't be 0, which means x can't be 0. So the domain is going to be this, except I have to leave the 0 out. I have to exclude the 0. So it's going to go 0 to 2, union 2 to infinity, not including the 0 this time. Okay, and then I might simplify this by doing a flip and multiply. This is over 1, and this is 1 over x minus 2 times 1 over square root x, which would be 1 over square root x times x minus 2. Composing functions. Another way to combine functions is when we use the output from one function as the input for another function. For example, suppose that we define the functions f and g as follows. We have a discount function, g of x, that's x minus 20. It finds the sale price after a $20 discount. And then the sales tax function multiplies your price times 1.0625, and that tells you price after tax. So does it matter if we find the sale price first or the total cost first? Yes, it definitely matters. Let's just say something costs $100. So if we take $100 and discount it $20, we get $80. And then I'm going to multiply that by 1.0625 to calculate the tax. That's $85. So I'm going to put up here, I'm going to say $100. Discounted becomes $80. Add the sales tax becomes $85. Okay. But if you do it in the other order, okay, we start with the $100. If we calculated the sales tax first, 100 times 1.0625 is $106.25. Okay. Then we take our $20 off and it becomes $86.25. Okay, so you get different values for what you have to pay depending on the order you do this. So yes, order matters when you are composing two functions. When we purchase a taxable item at a store, the sale price is calculated first. So that's how it usually works. You calculate the sale price by subtracting the discount, and then the total cost is determined by adding the sales tax to the price. So we can use a sequential process to combine these two functions to make a new function that gives the purchase price of an item after the discount has been given and the sales tax has been calculated. This process is referred to as a composition of functions and is represented with this notation f circle g of x, and you would read that as f composed with g of x or f of g of x. So let's examine the order of performing a composition of the functions f and g, familiarize ourselves with the language. So x is the input of g, okay? So you plug the x into the g function, then you take the result and plug that into the f function. So it's very important to understand the order of operations when evaluating a composite function. Start with the innermost parentheses first and work your way out. So for example, we take the x is the innermost parentheses, so we're going to apply the g formula to the x, take the result and apply that to f. If we first calculate total cost, including sales tax, and then apply the discount, this composition would be g composed with f, or g of f of x. So let's see, if we want to find the domain of the composite function f composed with g, x has to be in the domain of g, and g has to be in the domain of f, because that's what the order says x goes into g, then the result, g, goes into f. So x has to be able to go into g, and g has to be able to go into f. Okay, hopefully this will all get a little clearer with an example. So I have f of x is x squared, and g of x is 1 over x plus 1, and I want to evaluate f composed with g of 3, which means f of g of 3. So you work on the innermost parentheses first. So I take this 3 and I plug it into the g formula. So I'm going to put a 3 into g. So g of 3, so this is going to be f of g of 3, which would be 1/4. Okay, if you put a 3 into the g formula, you get 1/4. Now I'm going to take that 1/4 and put it into the f formula. So I'm going to take my 1/4 and I'm going to square it because f of x is x squared. So 1/4 squared is 1/16. Now I'm going to do this in the reverse order. I'm going to do g of f of 3. So first I'm going to take my 3, it's the innermost parentheses, and work my way out. So I'm going to take my 3, plug it into the f formula. So f squares things. So this is going to be g of 3 squared, or 9. And then g of 9, I plug 9 into the g formula, and I get 1 over 9 plus 1, or 1/10. So again, you can see that these came out differently. The order that you apply f and g matters. Okay, so conclusion, f composed with g is generally not equal to g composed with f. I want to determine a general expression for the composition function f of g of x. So f of g of x. So g of x has a formula, 1 over x plus 1. These two things are equal. So I'm going to replace this g of x with its formula. So I have f of 1 over x plus 1. And then function notation means whatever you see in this parentheses after f means that in the formula for f, you're going to replace every x with 1 over x plus 1, with whatever shows up in this parentheses. So this is going to be, instead of f of x being x squared, f of the stuff is going to be the stuff squared. So it's going to be 1 over x plus 1 squared, which is the same thing as 1 over x plus 1 squared. And then I want a general expression for g composed with f. So go the other direction, g of f of x. So in the innermost parentheses, I'm going to replace f of x with its formula, right? Up here, I replaced f of 3 with a number. I can't get a number. This is a general f of x, so I'm going to replace it with its formula. So this is g of, the formula for f of x is x squared. And then the function notation says, if you replace the x in parentheses of g with an x squared, or anything, you have to replace every x in the formula for g with whatever you put here. So this is going to become 1 over x squared plus 1. How to find the domain of a composition. We're going to do the domain of g of f of x. So it says find the domain of the inside function first. So g composed with f, that means g of f of x. So the inside function is f, which is x squared, and its domain is all real numbers. So I'm just going to shade all of this. Okay, second step is find the domain of the outside function, g in this case. So g has a domain of all x's except -1, because you can't put a -1 in that denominator. So here's my -1. I put a big open circle there, but I shade everything else. And then the third step says set the inside function equal to the excluded values found in the second step. So my second step, the excluded value is -1. My inside function f of x needs to get set equal to -1. So I would set x squared equal to -1. And then I have to solve this, but there is no x squared. There is no x that when you square it, you'll get -1. So this is no solution. So there are no additional excluded values for x. So the domain of the composite function is all real numbers. Okay, that can be a little tricky to wrap your head around. Like, why is -1 not excluded from the domain of the composite? I'm going to draw a little picture to help us. Okay, I like to think of functions as machines. So I'm trying to do g of f of x, which means g of f of x. So F is the inside function. I like to think of this as the first machine. So X is like the input. You're going to drop it into the F machine. Okay, so I do that first because you always do the innermost parentheses first. So this is a little machine, the F machine. I drop an X in, and out comes an X squared because F of X equals X squared. Okay, so that's my first machine. It takes X's and turns them into X squareds. There are no restrictions on this machine. You're allowed to put any X you want in. You'll never jam this machine because F can square anything, right? There's no number you can't square. So F never jams, okay? Then I'm going to take the result from F and drop it into the G machine. So here's my G machine. I take my X squared, I drop it in, and out comes 1 over X squared minus 1. Sorry, plus 1. Okay. So this is an unjammable machine, F. F is unjammable. Okay, so that means I can plug any X in. So no restrictions on the domain. Okay. Now G, like I have to be careful not to make this denominator 0. Okay. But there is nothing I could get from the F machine and put it into G that would make this denominator 0. Okay, the only thing that would make this denominator 0 is if X squared were negative 1, but that's impossible, right? There's no way you could get something out of F that would jam the G machine. Okay, so G jams if you put negative 1 in, but the thing you're putting in, X squared, will never be negative 1. Is never negative 1. So no additional restrictions. Needed. Okay, so I can put anything I want in up here, run it through F, and then the result can always go through G. It will never jam up the G machine because it would never produce something that gave a 0 in a denominator.